Okay, so welcome everybody to the third talk of this morning. It's by Edward Bierstone, and he will talk about partial desingularization.
Thank you very much. I'd also like to thank the organizers for their very kind invitation. So it's a real pleasure to see so many friends here and to participate in a live meeting for the first time in over 2.5 years. So the project that I'm going to talk about is work in progress together with my collaborators, Andre Bellato, and my student, Ramon Ronson. It's in the general area of resolution of singularities, which of course has been discussed in many presentations in this program, particularly from the point of view of how to transform a mapping or a variety into an object which is locally monomial or normal crossings. So from this point of view, I think that it's very natural to ask the following question. If we're given a variety, let's say an algebraic variety or a complex analytic variety, can we find a sequence of blowings up so that the composite sigma of that blowing up sequence preserves the normal crossings locus of the original variety, and such that the final transform also has only normal crossing singularities? So that's a basic question. Normal crossings at a point means, of course, that locally x can be defined by a monomial equation in terms of local coordinates. But the question is ambiguous because the definition of normal crossings depends on the meaning of local coordinates. So, for example, local coordinates may mean what are called regular coordinates or a regular system of parameters. In this case, normal crossings means in particular that locally every irreducible component is smooth and the components are mutually transverse. So with this notion of local coordinates, the normal crossings condition is usually called more precisely simple normal crossings. But of course, local coordinates may mean simply local analytic or étal local or even formal coordinates. And usually, for example, when we talk about étal coordinates, we even admit the possibility of a finite field extension. And so this is the more general notion of normal crossings. So for example, if we take the nodal curve, y squared equals x squared plus x cubed, 0, this is -1. The singularity at the origin is normal crossings, but it's not simple normal crossings. And likewise, if we take the very simple equation, y squared plus x squared equals 0, this is normal crossings, but it's simple normal crossings if and only if the square root of -1 belongs to the ground field. Okay, so this is the difference between the two notions. And in fact, the answer to the question really does depend on the distinction between these notions. The answer is yes for simple normal crossings. In that case, it goes back to work of mine together with Pierre Millman in 1997. It was also proved by Szabo, and there have been several more recent proofs by Kolar and by others. Kolar also pointed out that with the general definition of normal crossings, the answer is in general no. And a very simple example is given by the Whitney umbrella. So the Whitney umbrella has twofold normal crossing singularities along the non-zero W-axis, but it has a non-normal crossing singularity called a pinch point at the origin. And the fact is that there's no proper birational morphism that eliminates the pinch point without modifying normal crossings points. It's very easy to see that because at a non-zero point of the W-axis, there are two smooth local analytic branches. And if, for example, we go around a little circle about the origin in the W-axis, then the two branches are interchanged. But that phenomenon will certainly persist after a birational morphism, which is an isomorphism over the generic point of the W-axis. And so that means we cannot eliminate the pinch point singularity without modifying the normal crossings locus. Okay. Nevertheless, in fact, for surfaces in the two-dimensional case, that's really all that can happen. So a theorem that Pierre and I proved in 2012 says that for surfaces, there's always a smooth blowing up sequence preserving the normal crossings locus, such that in the end, the strict transform has only normal crossings and pinch point singularities. Okay, so it's in this context that I want to look at the general problem. One very important remark, the Whitney umbrella has smooth normalization because if we set W equals V squared, then the equation Z squared minus WX squared splits into two factors of order 1. And in fact, the morphism restricted to any of those factors is a normalization of the Whitney umbrella. The morphism restricted to either of those factors provides smooth normalization. So normalization, of course, played a very important role in classical approaches to resolution of singularities. And in particular, if you have smooth normalization, then that gives a relatively simple one-shot process to resolve singularities. From the point of view of the results that I'm going to describe, I think that it's very natural to make the following conjecture, that given any algebraic or complex analytic variety, there's always a finite composite of smooth blowings up, which preserves the normal crossings locus, and so that the final transform has smooth normalization. So this partial desingularization is would really be almost desingularization. In fact, we don't really have an abstract approach to this kind of question. And our approach is rather more concrete, as suggested by the Whitney umbrella example. So a second, more concrete conjecture would be that this can be achieved in such a way that the final transform has only singularities from an explicit finite list, which I'm going to try to propose. And this explicit finite list we will call minimal singularities. Okay, and I'm going to describe some general techniques from which at least we can prove the conjectures in the case that the dimension of the variety is less than or equal to 4. And maybe it's worth, since I stated the theorem for surfaces, to give a simple proof in the case of surfaces. So first of all, I'll explain a little bit later on that in general, we can reduce to the case that our variety is a hypersurface. So in this case, there may be triple normal crossings points, which are isolated. And there are double normal crossings points, perhaps, and the locus of such points has codimension 2. If we apply the resolution of singularities algorithm in the complement of the triple normal crossings points, we can run the machine without modifying double normal crossings until we get to the situation that the maximal value of the desingularization invariant, it's not important what it means, equals the value that it takes at double normal crossings points. At that point, the resolution of singularities technology tells us that the locus of points where the invariant equals its value at a double normal crossings point is a smooth curve. Moreover, at any point of that curve, we can choose local coordinates in which the variety is defined by a very simple equation, z squared plus w to the k times x squared equals 0, where w is the exceptional divisor, which we've introduced now at this point. In particular, this equation says that x is double normal crossings on the non-zero w axis. Of course, if we have this equation, z squared plus w k to the x squared, we can simply blow up the origin a finite number of times, and then according as k is even or odd, we will get double normal crossings or a pinch point. So that's a very simple proof of the theorem in two dimension. Resolution of singularities proof. But in fact, this proof doesn't really illustrate a second very important phenomenon, which is going to appear in higher dimension. So, of course, once resolution of singularities told us that we could reduce to an equation of the form z squared plus w to the k times x squared equals 0, we already know that the defining function here splits into two factors, but as a polynomial in the fractional power w to the 1/2, as well as x and z. Okay. So the proofs of our main results are actually going to be combinations of methods from resolution of singularities and such splitting techniques. In fact, I'm not going to talk about the resolution of singularities part. I'm going to concentrate on the splitting techniques part, partly because I think that there are very interesting questions that I want to discuss, and also partly because this part of the techniques are related to the work of several other speakers in this workshop. In particular, I think that Mikhail Matushinsky is going to talk about very related things this afternoon. And the work is also closely related to work of Adam Parashinsky and Guillaume Rond in their approach to the Biancard-Young theorem. Okay, but before I get into this splitting stuff, what is the higher dimensional analog of the Whitney umbrella? Circulant matrices appear in many areas of mathematics. The circulant matrix CK is a k by k matrix with k indeterminates in the first row, and the remaining rows obtained by successively cyclically permuting those coordinates. It's very easy to see that such a circulant matrix has eigenvectors given by powers of the kth root of unity, the 2 pi I over k, and corresponding eigenvalues, which are linear combinations of the indeterminants with these powers of the root of unity as coefficients. let me call the determinant of this circulant matrix delta sub k, and we would define a function by the formula that I've shown. So it's the determinant, but with fractional powers of w. So it's a function of w and the x's, and because the determinant is the product of the eigenvalues, it's given by this formula, which is right away a splitting formula involving fractional powers of w. It's very easy to see that this is an irreducible polynomial in w and the x's just from invariance with respect to the cyclic group. This, I claim, is the higher dimensional version of the pinch point, the singularity at the origin of the Whitney umbrella. So of course, it's clear from the formula that this singularity that we call a cyclic point of order k is a limit of k-fold normal crossings points in k plus 1 variables, the w and the x's. And the circulant singularity of order k has smooth normalization because it splits on substituting w equals v to the k. For example, this perhaps the k equals 1 cases by convention, but the circulant singularity of order 1 just means smooth. The circulant singularity of order 2 is the pinch point, z squared minus wx squared equals 0. Of order 3, for example, is given also by a very nice equation, z cubed plus wy cubed plus w squared x squared minus 3w xyz. And the formula, of course, becomes rapidly more complicated in higher dimension. So the minimal singularities, which we propose as the finite list, which has to be admitted, consists of products of circulant singularities and their singular neighbors. Of course, if we can't get rid of circulant singularities, we can't get rid of any neighboring singularities either. So their neighbors do have to be allowed. The next dimensional example of this phenomenon is the case that x is a hypersurface in 4 variables, so dimension x equals 3, that I proved together with Pierre Leray in 2012. So we verified the conjecture B with the following list of minimal singularities. So first of all, what are the neighbors? What are the neighbors of the circulant singularity of order 3? Of course, the neighboring singularities include double normal crossings and triple normal crossings, but they also include an order 2 singularity, which occurs at non-zero points of the x-axis for the formula that I wrote at the top of the page. And this is a picture of that singularity. And the complete list of minimal singularities in dimension 3 consists of the circulant point of order 3 and its neighbors, together with, of course, all normal crossing singularities up to that order, so up to order 4, the circulant point of order 2, and the final one in this list, which I've denoted smooth cross a circulant point of order 2, but the product really means not product of varieties, but product of the defining function, so product of ideals. Okay, so this singularity is defined by y times the pinch point, z squared minus wx squared equals 0. And of course, it is a limit of threefold normal crossings, as is CP3. Okay, so this is the complete list of minimal singularities for dimension x equals 3. Maybe I don't want to spend too much time on this slide, but here is the complete list of neighbors of circulant points of degree 4. So for example, the first two in the list are singularities of order 3 and order 2, which occur at non-zero points of the x3 axis and of the x2 axis. The final singularity in the list occurs at points of the x2, x3 plane, which are not on the axis. The reason that it's possible to write down a unique normal form for the singularity at any point in these subsets is really a question of it's really a reflection of the fact that this circulant function, the circulant singularity, is homogeneous in two different senses. As a polynomial in the x's, but also weighted homogeneous as a polynomial in all the variables. And there's one other singularity in the list, which I've called 2', which actually is not a neighboring singular point of the circulant point of order 4. And the reason that it's in the list is that if we include all the neighboring singularities, those neighboring singularities may themselves have limits that we cannot get rid of. And so when we say neighbors of CPK, we mean neighbors in that somewhat more general sense. Actual neighboring singularities and limits which will persist. Okay, so this is just to point that out. And it's possible to write down in a very simple way the complete list of minimal singularities in the dimension 4 case. Okay, but let me, as I said, set aside resolution of singularities techniques for the moment, though I'll try to tie things up a little bit in the end, and talk about the splitting techniques which will intervene in our approach to these conjectures. Okay, so first of all, I want to put ourselves in a kind of local context, which really comes from resolution of singularities, the possibility of making certain preliminary reductions. So first of all, we can assume that our variety is a hypersurface because normal crossing singularities are hypersurface singularities, and the desingularization algorithm always blows up points of highest embedding dimension. And so if we can reduce to the case of a hypersurface without modifying normal crossings points. So we want to understand what happens at limits of k-fold normal crossings points. And we can make a preliminary reduction to the case that x is described by the vanishing locus of a single function. It depends on many variables, but we can assume that f locally has the form of a monic polynomial in Z with coefficients which are regular functions in the other coordinates. And using resolution of singularities, we can reduce to the case that the function is generically k-fold normal crossings on the subspace where x and z vanish. So the normal crossings points are normal crossings with are functions which have linearly independent gradients with respect to x and z. Following the desingularization algorithm, we can assume that the invariant takes the same value that it has at normal crossings points at every point of x equals z equals 0, and that the normal crossings locus is given by the complement of a monomial in the divisor in x equals z equals 0. So f is generically k-fold normal crossings in UW space in x equals z equals 0. But the non-normal crossings locus is always an algebraic subvariety. So using resolution of singularities, we can assume that the non-normal crossings locus is given by a monomial in certain exceptional coordinates. Those are the variables w. So that's the breaking up of the variables into u, w, x, and z. Okay, but I want to begin with this context. Okay, and what we're interested in is the splitting of f into linear factors. So in other words, in finding the roots of this monic polynomial in Z. I'm going to use notation which has been used in many talks here. So round brackets means the field of fractions, so single round brackets, the field of fractions of polynomials in W, or double round brackets for formal power series. And the overline denotes an algebraic closure. So for example, an algebraic closure of the field of fractions of polynomials in W can be embedded as a subfield of an algebraic closure of the field of fractions of formal power series, and it is the subfield of elements which are algebraic over the ring of polynomials. Okay, of course, if W is a single variable, then the field of fractions of the formal power series ring consists of formal Laurent series with finitely many negative exponents, and its algebraic closure can be realized according to the Newton-Puiseux theorem as fractional Laurent series. Let me before presenting any results, discuss a very basic example which kind of illustrates at the same time what we want to accomplish and why the results that I'm going to describe can't really be improved. Okay, so let's consider this polynomial in three variables, z squared plus w cubed plus x times x squared. So this is double normal crossings on the non-zero w axis. The polynomial f doesn't split with roots that are formal power series in w and x. But if you substitute w equals v squared, then we see that the original polynomial does split with roots that are formal power series in x, but with coefficients which may involve denominators in W to the 1/2. With coefficients which are Puiseux series. This function f, or f of v squared xz, is of course not normal crossings as an element of the ring of formal power series in 3 variables, but it is normal crossings as a power series in xz with coefficients in the field of fractions of polynomials in V. Now, so F splits with coefficients which are Puiseux series, as I said, but what's very important about this splitting is that the powers of W or of V in the denominators grow at most linearly with respect to the degree with respect to X in the numerator. And because of that, we can simplify things by blowing up the origin. So if we blow up the origin, then the normal crossings locus, well, first of all, it lifts to the W chart, which is given by the substitution W, WX, WZ. And in that chart, the strict transform is given by composing by that quadratic substitution and factoring out W to the power 2. And what we get is this polynomial z squared plus W times W squared plus X times X squared. And of course, if we repeat the process twice more, then we will get a polynomial now, z squared plus W cubed times a unit times X squared. So even though we originally only had splitting as formal power series in X with coefficients which are Puiseux series, here we actually have splitting as power series in both the fractional power of W and of X. And that's what we're looking for. That's what we're looking for. In fact, in this example, it's very to see that after one additional blowing up with center Z equals W equals 0, we get a pinch point as we want. Okay, so this is a kind of basic example of what we're trying to accomplish. Okay, so let's go back to the general setting. So recall that we can begin with the assumption that we have a monic polynomial in Z with coefficients that are regular functions in the other variables. We're assuming that F is generically normal crossings on X equals Z equals 0. In fact, normal crossings outside of a monomial in the exceptional divisor. And we're interested in a splitting, hopefully with roots which are formal power series. Okay, so a couple of simple preliminary comments. From the generic splitting condition, it's easy to understand that there's a unique splitting which are with roots which are formal power series in U and X with coefficients in the algebraic closure of the field of fractions of polynomials in W. In fact, each of these roots belongs to the ideal generated by the X's. But we haven't got rid, we certainly haven't got rid at this point of powers of W in the denominators. And one other thing, if we want to use a very little bit of Galois theory, it follows in fact, that our monic polynomial splits as a polynomial as a formal power series in U of X with coefficients in a finite normal extension of the field of fractions of polynomials in W. For example, if we have a single variable W, then F splits with roots which are formal power series in U of X with coefficients which are Puiseux series in W. And in fact, we can even take P equals K if F is irreducible. Okay, so the theorem which we would like to prove, we can so far only prove if there is no U variables and one W variable. So that's the case Q equals 0 and R equals 1. And according to the setup, this is what we need to describe limits of n-fold normal crossing singularities in K plus 1 variables. Okay, so in that context, that means we're assuming that F is a monic polynomial in Z with coefficients which depend on K variables, W and the K minus 1x variables, which is normal crossings generically on Z equals X equals 0. In fact, in the complement of the exceptional divisor given by the W coordinates. And we can prove that after a finite number of blowings up of the origin, F splits as we like, where the roots are now formal power series involving fractional powers of W. So our proof of this, which I'm not going to say very much about, but it uses the first splitting condition here, together with a multivariate version of the Newton-Puiseux algorithm due to Soto and Vicente from 2011. And what we believe is true in general, though we might be too optimistic unless we impose an additional hypothesis. So remember, we can begin with the assumptions that I said, but also from the resolution of singularities algorithm with the assumption that on the UW subspace on X equals Z equals 0, the invariant takes the value that it takes at a K-fold normal crossing split. So the conjecture is that perhaps with that additional assumption, after finitely many blowings up with particularly simple centers, so centers in Z equals X equals 0, but centers which are codimension 1 defined by exceptional divisors within that subspace. After a finite number of blowings up with such centers, we speculate that we can assume in the same way as in the theorem above that F splits as a genuine formal power with roots which are genuine formal power series in U of X involving fractional powers of W. A less optimistic version of this would be to allow blowings up still only with combinatorial centers, with centers given in the maximal context subspace z equals x equals 0 by exceptional coordinates z equal to 0. But from the way we want to use the theorem, there would be great advantages if it's really true in this stronger form. Okay, so I want to finish simply by tying this splitting business into what comes out of resolution of singularities, and in particular, tying it together with the notion of circulant singularity that I mentioned earlier. So from this splitting theorem and using resolution of singularities techniques, we can show that with the additional hypothesis that the invariant at 0 equals its value at a k-fold normal crossings points, there's a finite sequence of admissible blowings up which preserve the k-fold normal crossings locus as we want for our theorem, after which the only singularities that can occur as limits of k-fold normal crossings points are products of circulant singularities. In fact, this can be said in a very precise way. So by a product of circulant singularities, I mean, again, the 0 locus of a function which is a product of the circulant functions that we defined at the beginning, but where all of the variables which occur in each of the factors are independent indeterminates. So there are no repeated variables among the factors except for W, and it's the W axis, which is the k-fold normal crossings locus. Okay, so of course, this theorem expresses what we're really after, which is by a finite sequence of admissible blowings up, reduced to the situation where we have only minimal singularities from an explicit finite list with smooth normalization. And this theorem is obtained using resolution of singularities techniques, but from the previous splitting theorem. Okay, so both the desingularization and the splitting techniques seem to be very important in this business. So as far as the case of 5 variables is concerned, so this is dimension x equals 4, then in fact, both of these theorems can be used together with desingularization techniques to prove our main conjectures. And analogs of the theorems for arbitrary Q and R, so for an arbitrary number of U and W variables, are the main ingredients that we need for the conjectures in general. In fact, if you think about the 5 variable case, then you actually do need some cases of theorems 1 and 2 where there are more U and W variables. You will need these theorems with Q less than or equal to 2 and R less than or equal to 2. To study limits of triple normal crossings and double normal crossings points in 5 variables. But these we can handle in a rather different way using the discriminant of f in its relation to the coefficient ideal. in the way that it comes into the Bierstone theorem. Okay, so in that way, we at least recover we get the main conjectures in low dimension. So I spoke unnecessarily quickly. Sorry, and that's all I wanted to say. Thank you very much.
Thank you very much for the nice talk. Are there any questions or comments?
About the general case that you're trying to treat, what kind of splitting would help to achieve the, in the general case that you're trying to treat? What kind of splitting could help to?
So really, what I said is really what I said here is the optimistic conjecture is precisely the result that we need.
But so this kind of splitting would be enough to.
I don't want to say that if we have a proof of this conjecture, then we have a proof of our main conjectures. But I think that the resolution, I think that the techniques which have to be developed using resolution of singularities methods are of a technical nature, whereas I feel, maybe I'm wrong, you'll explain otherwise, that something new is really needed for the conjecture on this slide. Okay, and that's why I wanted to emphasize these splitting techniques.
Okay.
So, there are some new results on resolution of singularities by Abramovitz, Temkin, Wodasik, and then McQuillan, where they use weighted blowups. And in this way, you respect the normal crossing locus by introducing eventually some quotient type singularities in your Hammett space. So I was wondering if by studying this quotient singularities that you get in your Hammett space, you could also, but I know that it's true in the case of the pinch point, that you can obtain a pinch point as a quotient singularity by z over 2z, right? So yeah. I was wondering if you can make the same catalog by studying this quotient singularities that you get after the weighted blow-up process.
Yeah. We've also been wondering, but in fact, from the look that we've had at trying to understand the relevance of weighted blowings up to this problem, it's not, at least at this point, it's not clear to us how much of a help that would be. But you know, perhaps.
Because, well, this pinch point type singularities, they appear very naturally when you look at the, let's say, the quotient type singularities that you get by this new procedure.
Yeah, no, that I understand that. I understand that that's correct.
Okay, so are there further questions, comments online? Okay, seems not to be the case. So let's thank the speaker again. And we have lunch break and resume at 2:30.